Welcome back to Integral Calculus. In this video, I kind of have to duck my head out of the way so you can read the whole title. We're going to be looking at integrals involving inverse trigonometric functions. I don't have a lot to say in introduction, so let me get my head out of the way and we'll dive right in. Just for the sake of simplicity, I'm going to focus on tangent. I think that's the easiest one to understand, and show you a little bit of where these formulas came from. And then we'll just put the other ones down for the sake of completeness. But we know from our previous study that the derivative of the arctangent of u is u prime over 1 plus u squared. Rearranging this, let's just flip the equation around. And then integrate both sides of the equation with respect to x. On the right-hand side, why did I write a u there? Getting ahead of myself. On the right-hand side, fundamental theorem of calculus says that the integral of a derivative is the original function, or possibly off by a constant of integration. And on the left-hand side, we can do a u substitution because u prime dx is just du. All right, so technically speaking, that's it. That's a formula for the anti-differentiation rule involving arctangent. But I would love to be able to do a little bit better. Specifically, the fact that we have affixed here a constant 1 is a little bit annoying. I would love to be able to generalize that. And in order to get there, I'm going to multiply both sides of the equation by 1 over a. How do I know to do this? Well, somebody much smarter than me figured this out quite some time ago, and I'm just copying their work. Remember that c is an arbitrary constant. Multiplying an arbitrary constant by a constant gives you a new constant, but it's still an arbitrary constant. Right? That's one of the tricks that shows up all the time in working with calculus that confuses students. The c in this line and the c in that line are not the same number, but they are both arbitrary and can be chosen to be whatever we want them to be, so we don't worry about it. On the left-hand side, we can't quite work that nicely, but we can bring that constant inside and distribute it across the denominator there. At this point, we've made quite a mess of things. We started with something that seemed straightforward, and we ended up with something a lot less so. I don't quite have that, but it would be really nice if I had a way of substituting here again. And we've already done a u substitution, so the next letter, I guess, would be v. So we'll do a v substitution. Let v equal au. It would be really nice if I had v squared, which is a squared times u squared, sitting there in that spot in the denominator. Unfortunately, instead I have a times u squared, which is not quite so nice. But I'm not going to let that stop me. Because if I want to do this substitution, I'm also going to need to know what dv is. And dv is going to be a times du, which means I need to get an extra a here. And one way I can get an extra a there is multiplying the numerator and denominator by a. So we get a times du in the numerator, we get a times a, which is a squared, and then a times a u squared, which is a squared u squared, in the denominator. And there we have it. The integral of dv over a squared plus v squared is equal to 1 over a times the arctangent. Well, I said it was u here, but if I just take that equation and rearrange it, u is equal to v over a. Finally, it looks kind of silly with v's there, so I'm going to substitute back and write this in terms of u so that it looks the same as all of my other anti-differentiation rules. For the sake of brevity, I'm not going to, but I could do the exact same thing with sine and with secant. Doing so would give me the rules. Integral du over the square root of a squared minus u squared is arcsine of u over a. And integral du over u times square root u squared minus a squared is 1 over a times arcsecant of absolute value of u over a. So a couple of minor things to pay attention to. Places where lumping these together tends to get students a little bit mixed up. In the arctangent and arcsecant formulas, there is a 1 over a in front. That does not show up for arcsine. Arcsine and arctangent have u over a in the argument. Arcsecant has an absolute value of u there. That one makes a little bit more sense. If you remember, the differentiation rule for arcsecant has an absolute value that shows up there. So absolute value with arcsecant. That's also something that we're somewhat familiar with because integrals involving secant itself will have natural logs, and natural logs always bring absolute values with them. I'm going to go ahead and jump right into the hard case. The easy cases, where you can just see things and play a matching game, we tend to be happy with. We don't worry about too much. It all works out, and we're able to get through things. The biggest point of power of the inverse trigonometric functions are expressions where it is completely unintuitive that this is something that we're going to want to be able to do at all. The integral of dx over the square root of 6x minus x squared. Having just introduced you to the integration rules for inverse trigonometry, this probably isn't jumping out at you as something even worth considering in that aspect. But there's a rule of algebra that you were introduced to quite some time ago. It probably came up in 2 or 3 or 5 courses, and you kept hoping that it would go away. And it never went away, and every time you thought you were done with it, it came back again. Completing the square. I'm going to take the radicand, the stuff underneath the square root, and write it in a complicated format. Negative outside, x squared minus 6x. The rules for completing the square say that you have a first term with an x squared, a middle term with an x, and a constant term which is initially blank. Take the coefficient on the middle term, in this case negative 6, half of it, negative 3, square that, positive 9. Add 9. By doing that, the negative out front stays a negative out front, but the stuff inside the parentheses is now a perfect square trinomial, and it will factor to x plus the thing that you squared, in this case negative 3. The whole thing squared. Every time that works. But we can't just arbitrarily add 9. That doesn't work. That doesn't fall into the rules of algebra. So we have to balance it. Notice that there's a negative out here that would be distributed through, so that's really a negative 9. To balance it, we need to introduce a positive 9. And if you simplify that expression, 9 minus the quantity x squared minus 6x plus 9, you can verify that you end up with 6x minus x squared, which is what we had at the start. Then, for convenience, I'm going to rewrite that 9 as 3 squared. I'm going to bring everything back into the integral in this form. And now it's starting to look a little bit more like the integration rule for inverse sine, right? The integral of du over a squared minus u squared. Our a in this case is 3. Our u is x minus 3. And from that, du is just dx. That substitution will turn this integral into the integral of du over the square root of a squared minus u squared, which is exactly what gives us the inverse sine, arc sine of u over a plus c. Just fill in our particular values of u and a, and this integral is going to become the arc sine. I don't need bold font. The arc sine of x minus 3 over 3. More often than not, when you're looking at trying to do an integral like this on your own, you're going to see something that's already in a form like this. But being able to look at that more complicated case, where it's not immediately obvious, and saying, I wonder if there is something there. If we come back to our general rules here, the key ideas, having a fraction, especially having a fraction with a square root in the denominator, you start to wonder, can you write this as the sum or difference of two perfect squares? It's not always the right answer, but it's something to try. It's another tool to add to your bag of tricks that you can pull out every time you need to evaluate an integral and the antiderivative is not immediately obvious. All right, let's end with one for you to try on your own. How about the integral of 2x dx over 12 plus x to the fourth power? Take a couple of minutes, see what you can do with this one. Rely on the hint that it came in the video on integrals involving inverse trigonometric functions, and I'll see you in the next one.